Hello everyone, welcome to Electronically Connected. In this video, we will be discussing what a combinational logic is, a brief introduction of what a combinational logic is, followed by the most important combinational logic block, which is a multiplexer. We will be diving into multiplexer and discussing how a structure of multiplexer is and what are different types of multiplexer, that is 2:1 MUX or 4:1 MUX. So let's get started. So let's start with what is a combinational logic. A combinational logic block is basically a block which is made up of some logical gates. So we know what are logic gates, that is AND, NAND, OR, NOR, XOR or XNOR. So this is my combinational circuit. Let's take this as a block which has some number of inputs. These are my inputs. And then it has some number of outputs. So this is in brief what a combinational logic is. So it is basically a combination of different logic circuits. The outputs depend on the inputs present. Let's see some of the properties of a combinational logic. So we know that the output depends on the input. Okay. Then this has no memory. So it does not matter what the last input was for one particular logic. So it depends on the present input. So there is no memory. Also, we have n number of inputs and m number of outputs. Now, what are these combinational logic circuits used for? These are used for different types of operations like data manipulation, and then we have error detection, arithmetic logics like for ALU or adders or subtractors, and then we have coding or decoding or changing from one code to the other, and many other operations. So let's see the most commonly used combinational logic, which is called a multiplexer, also called as MUX. So we have MUX, which stands for MUX. So let's see a multiplexer, that is also short for MUX. A MUX is the most commonly used combinational logic. So how does it operate? So we have, let's say this is my MUX. This is my MUX. As a combination logic, it has number of inputs. So these are my inputs. It has only and only one output. And it has something else. It's called select lines. It has some select lines. Let's see how do we define these inputs and outputs and the select line. So in a MUX, always there's only one output. Now, the number of inputs are 2⁻n. So we have 2⁻n inputs. This here is 2⁻n number of inputs. And the select lines are this n. We have n select lines. Let's take an example. If I say we have 8 inputs, I have 8 inputs. So what does that mean? We have 2⁻3 inputs, correct? Because 2⁻3 is 8. So these are my number of inputs. And this 3, we have 3 select lines. And always we have one output line. And with this configuration, a MUX is written as 8:1 MUX. That means input is to number of output MUX. And this value of 2⁻n can be anything. It can range from 2⁻1 to 2⁻n. And n will always be the number of select lines. So let's take an example and see the logic behind how to define a MUX. Let's start with something called 2:1 MUX. Now what does 2:1 MUX mean? That means we have 2 inputs and 1 output. So let's see the logic behind this. How do we write it? We have inputs D0 and D1. These are my inputs. I have my select line S. This is my select line. And I have my output as Y. So the logic behind how to write a 2:1 MUX is the output logic is output is equal to S bar D0 plus S D1. Now how did I get this value and what does this mean? This means that whenever the value of S is equal to 0, then the output of my Y that I'm going to get is D0. And whenever the value of S is equal to 1, then the output of Y that I get is D1. So how did this happen? Let's see. So if my S value is 0, so what happens is S bar becomes 1 dot D0 plus S here is 0. So it's 0 dot D1. And according to the AND rule, we know 0 dot anything will give you 0. So we have 0 and 1 dot anything will give you self, right? So we have D0 and D0 plus 0, that is ORing. ORing anything with D0 is going to give you itself. So we have D0, hence the output Y. So in this case, we took our S is equal to 0 and our output is D0. So this is the logic behind our multiplexer 2:1 MUX. So it depends on what is the value of my select line. So the value of my select line, the select line decides what output is going to be present at the input. So if the select line again is 0, then the output gets D0. If the select line input 1, then Y, that is the output, gets D1. Let's see the block diagram of a 2:1 MUX. Let's see the logic circuit first. So what was our equation? We had S bar dot D0 plus S into D1. This was my logic behind it. Now let's try and implement this. So we have two AND gates. So let's take first our inputs D0 and D1. We have two AND gates. And both of these are ORed together. The output of these AND gates are ORed together, giving my output Y. So we have D0 and D1. Now let's see the S. So we have S over here. Let's draw my S. The S goes simply as it is in this AND gate with D1, but it gets NOTed when it goes with D0. So we have a NOT gate over here and it enters. So this is my schematic diagram of a 2:1 MUX. So this is for 2:1 MUX. Now let's see the block diagram. How do we draw a MUX? Whenever we have a picture of a MUX, it is represented as a vertical trapezium. So this is how a MUX represents. We have two inputs. This is my two inputs D0 and D1. Here is my output Y and this is my select line. So this is how a 2, you can see with this diagram, we can see two inputs D0, D1. So 2:1 MUX. And let's see the truth table behind this. So we have S and we have output Y. So whenever my input S is 0, the output is D0. And when my S is 1, the output is D1. And there we have it. This is the most simple truth table of 2:1 MUX, where the logic behind is using two AND gates. The output depends on the select line. Now let us take another example, a more complicated one, which is called a 4:1 MUX. So we have a 4:1 MUX. Now what does 4:1 MUX mean? That means we have 2:2. We have 4 inputs. Let's call them D0, D1, D2 and D3. Here we have 2:2, so that means 2. That means we have 2 select lines. Let's call this S0 and S1. And because it's a MUX, and here we can see also 1, so we have 1 output. This is called Y. So we have a 4:1 MUX. Let's draw a MUX, which is a trapezium, which has an output Y. We have 2 select lines, S0 and S1, and we have 4 inputs. What are my 4 inputs? D0, D1, D2 and D3. And here we have it. We have our 4 inputs. We have a 1, 2, 3, 4, 4:1 MUX. Let's see the truth table of a 4:1 MUX. So we have S0, S1, and we have our output Y. What are the four possibilities? We have 0, 0, 0, 1, 1, 0, and 1, 1. Whenever S0 and S1 is 0, 0, the output at Y is D0. Then it goes D1, D2, and D3. And there we have it. Let's see what is the logic behind it. So what is the equation of our 4:1 MUX? Y is equal to S0 S1 bar dot D0 plus S1 bar dot S0 plus D1 plus S1 S0 bar dot D2, and plus the final one for 1, 1 combination, we have D3. So this is the logic behind, this is a logical equation behind my 4:1 MUX. So remember, a multiplexer, a MUX is a combinational logic circuit, and any combinational logic circuit can be implemented with the help of logic gates. So let's see our logical gate diagram. So we have four equations making the output equation. We have 4 AND gates. So let's make our first AND gate, second AND gate, third AND gate, and fourth AND gate. And the output of all of these AND gates are ORed together. So we have ORing of all of our outputs, giving one big OR gate, and we have output Y. And the inputs of these AND gates are D0, then we have D1, D2, and then D3. Now let us understand what is the how do we make our select lines. So we have S1 and S0. I'm going to make 2 NOT gates here. So S0 and S1 goes to the first AND gate. So we have S1 and then we have S0. To the second AND gate, only S1 bar goes, S1 bar, and from only S0. Now for third AND gate, we have S1 and S0 bar, and here we have our S1 and S0, and there we have it. This is the logical diagram for a 4:1 MUX using AND and OR gate. One of the best parts about using a multiplexer is that you can use a smaller multiplexer, let's say 2:1 MUX, to design a bigger multiplexer, let's say 4:1 MUX or an 8:1 MUX, or so on. So let's see how to design a 4:1 MUX using a 2:1 MUX. So we know that a 2:1 MUX will have 2 inputs and 1 output and 1 select lines. So let's draw a 2:1 MUX. So we have the very first 2:1 MUX and another 2:1 MUX. They're going to have their respective inputs, 2 inputs, D0, D1, and we have 2 more inputs remaining because it's a 4:1 MUX. So we have D2 and D3. And now we're going to have another 2:1 MUX whose inputs are going to be the outputs from my previous 2 MUXs. So here we have our select lines 0 and 1, and this is going to be my output Y dash. Again 0 and 1 for the outputs Y double dash. We're going to act as my inputs for 0 and 1, and this is going to give my final output. Here we're going to have a select line S1, and the same select line is connected to this one. So we have the same select lines S1 as here as well, and then S0. Let's draw the truth table of it. So we have a 4:1 MUX truth table which has 4 combination of my select lines 0, 0, 0, 1, 1, 0, and 1, 1, whose outputs are D0, D1, D2, and D3. Let's try and verify the working of one of this combination. Let's take 0, 1 select lines. So when S1 is 1, the output of the first MUX is going to be the input which is present at the 1. So we have D1 over here. And again, in this case, we're going to have D3. So we have D3. So D1 and D3 are going to act as my inputs for the second MUX. Now the select line is 0. So S0. So there we have it. D1 is going to be at my output and hence verified. Let's check the working with another combination. Let's check 1 1. So if saying 1 1, so that means my select line is again 1. So it's going to give D1 and D3 at the outputs, and D1 and D3 are going to act as inputs to the third MUX. Now my select line is 1. When my select line is 1, so D3 is going to get projected at the output and we're going to have D3 because the select line is 1. And there we have it. And hence, using this logic, any bigger multiplexer, let's say 8:1 or 16:1 MUX, can also be implemented using a 2:1 MUX or a 4:1 MUX, etc. So any bigger multiplexer can also be implemented with the help of a smaller multiplexer. With this, we come to the end of this video. In the next video, we will be discussing what is a demultiplexer and a decoder, and what is the logic behind the structure behind it and the circuits behind it. So do not forget to watch it. Please like, share and subscribe to my channel. Till then, happy learning. See you next time.